Good evening and good day, everybody. Great to see you all. Welcome to the 34th live episode of Ask Abhijit. Today we discuss science, physics, artificial intelligence, etc. So let's see who all is there. First of all, I welcome everybody. I welcome all the new members. Thank you very much for becoming members. Appreciate it. So who all do we have here? Subhash, Kakashi, Harshada, Abhilash, Jyoti Patel, Vivek Sinha, Dungar Singh Chauhan, Max Kopp, Akshay Debargia, Neeraj, Neha, Anshu, Abhishek, Harsh Pandey, Utkarsh, Apurva, Shubham, etc. Everybody, good to see you all. Great to see you all. So let's talk about physics and science, and let me start with your questions. Let's go to question number one. Okay, Aditya asks, how is a magnetic field formed in a galaxy? This is a great question. So, as we know, the Earth has a magnetic field. The planets, many of them in our solar system, have magnetic fields. The sun has a magnetic field. So, to understand how a magnetic field forms in a galaxy, let's try and first understand how it is formed in the Earth and in the sun. So, in the Earth, we know that the Earth has a liquid metallic core. The core is solid iron, solid metal, but around that there is a liquid component of the core as well. And this core is always swirling and it is metallic. And we know that metals conduct electricity. So it is this swirling and the metallic nature of this core that causes these uh, moving electric fields within the Earth. And we know that moving charges give rise to magnetic fields. So that's how the magnetic field of the Earth is formed. Now, when it comes to the sun also has a very powerful magnetic field. And the magnetic field of the sun originates in the convection zone inside the sun. So the convection zone is basically composed of solar plasma. Plasma is the fourth form of matter. It is also electrically conductive. It conducts electricity, and there is differential rotation inside the sun, which means that uh, at different depths in the sun there is different rates of rotation, and it is this different rates of rotation of the plasma, which is electrically charged, that creates this the powerful magnetic field of the sun. So the sun has a magnetic field, the Earth has a magnetic field, Jupiter has a powerful magnetic field because of similar processes. And eventually, the same way the galaxy itself has a magnetic field because of various phenomena such as supernovas, because of the individual magnetic fields of stars, because of the presence of plasma in the galaxy itself, etc. So it is all these different components put together that give rise to the galactic magnetic field. The galactic magnetic field is much weaker than the magnetic field of the Earth or the sun, but it is still there. So the processes are quite similar. It's always moving charges that create magnetic fields. It is the relativistic motion of electric charges inside a metal that gives rise to the phenomenon of magnetism, and so on. So basically, these are the processes that give rise to the overall composite magnetic field that is an intrinsic part of our galaxy itself. Okay, question number 2. Aditya asks, if aliens arrived right now and they were not friendly, what can we do? Do we stand a chance? Well, if aliens arrive right now, we are finished. We are royally finished. See, the thing is this: if aliens, let's take a look at us, our technological capabilities. Okay, as a species, as the human species, we currently are stuck on the planet. We have the ability to go into orbit, and once in the past, during period of time in the past, some of us have been able to go to the moon, and that too has been a superhuman Herculean effort to send people to the moon and bring them back safely. So that's the furthest that we have been able to go. We are still not in a position to reach Mars or Venus or any other part of our solar system. So we are basically still very much a planetary species. And that's the best that we can do with the current technology that we have. Now, imagine a species, a civilization, an alien species that has the technology, that has the technical capability to traverse interstellar distances and come to our solar system from another star system, which would be many light years away. That is an incredible leap of technology. That's a huge technological gap between us and them. So if these aliens were to arrive here, they would have technological superiority that is several orders of magnitude greater than ours. And therefore it is they would basically have technologies that are possibly inconceivable by us in order to be able to travel such distances, right? Because because we know that it takes years, at the speed of the chemical rocket, it would take like hundreds of years to reach even the nearest star from here, which is Proxima Centauri. So to be able to come here, they would have to be able to overcome that hurdle and many other technological hurdles. So that would give them enormous technological superiority over us. And therefore, if they were to come here and they would not be friendly, then we basically don't stand a chance against them, right? So that's why it is believed that we are kind of naive right now to be broadcasting our location and the fact that we exist here out into the universe via radio signals and various other signals. It may not be a very good idea because there may exist, well, dangerous species out there. So that's the short answer, that it is, if they actually do arrive here, aliens, and if they are not friendly, then we basically won't stand a chance. Dev Sharma asks, is it possible to dethrone a tech giant like Google, since it has invested billions of dollars in research and development, artificial intelligence, machine learning? Or is it possible to achieve that technology rapidly? You see, technology takes a long time to mature. Let's take a look at the story of Google itself. So, Google came into existence sometime in the late 1990s. I think it was somewhere around 95, 96, 97 that it first appeared on the scene, Google. I don't remember the exact years or whatever, but that's the time around which Google emerged. And when Google emerged on the scene, we already had these giant companies such as Microsoft and IBM, etc. At the time in the late 90s, Microsoft was the big dog on the block. I mean, nobody could even imagine competing with Microsoft. That's how big it was. That's the kind of monopoly that Microsoft had on the technology sector, computing, etc. So Google came onto the scene as a very small new startup started by two guys, two university dropouts essentially, right? And they had these new ideas, and they were able to acquire venture capital funding, etc. And because of their revolutionary new ideas and the technology they were able to implement and find funding for, within a few years they became a major player on the market. And since the 2000s, they have been investing in research and development in various technologies, like you mentioned. Nowadays, it's artificial intelligence, machine learning, a variety of algorithms. Now they're going into quantum computing, all that. So Google's story is at least 25 years old, I would say, right? So it took them that amount of time. It took them at least a decade before they became the number one company. So technology takes that sort of time to make a difference, to become mature. And even now the technology is ever evolving. So if one were to take the example of Google and how it dethroned somebody like Microsoft, then you can see it takes at least a decade for that to happen. So for a new startup company, for a new company, maybe in India, for example, if it were to try and challenge Google, it would take at least a decade. You can't do it overnight. It's simply not possible. You need to find new ideas. You need to come up with new ideas, revolutionary new ideas, the way Google came up with. Google came up with PageRank and semantic search and all those things. And later on, they came up with AdSense. So these were revolutionary new ideas. So to bring about the next revolution, one would have to come up with, first of all, ideas of that magnitude, which represent a quantum leap over what already exists. And then one would need to find the funding, the venture capital, and then one would need to iteratively improve the the technology. It takes time, lots of iterations for technology to mature. As you can see right now, we have this Indian startup or Indian social media company called Coup, right? Which is kind of a knockoff of Twitter, which is not a bad thing in any way whatsoever. You start by emulating the companies or the products that work well. You start by emulating them, and then you slowly over time try and improve upon that. So right now, the user experience on Coop, I have found it's not very pleasant, right? But I am not trying to by any way demean that. They are slowly trying to iterate upon what they have achieved and improve upon it. So over time, their user experience will change, it will improve. So that is the kind of thing that happens in technology. It takes time for a technological platform or any technology to mature. So it is definitely possible to dethrone a tech giant like Google, but it takes time. So you need focused effort, you need a long term vision, and you need proper focus on that. You need to be able to acquire funding and much more, right? So that's what needs to be in place for you to be able to dethrone a tech giant like Google. Akash says, please tell us about Ton 618 ultramassive black hole. How could it grow so large? I read somewhere that it shouldn't be this large as the universe simply did not have enough time to let a black hole grow this big. What could be its origin and how did we discover it as it lies so far away from us? So that's a great question. So this ultramassive black hole, Ton 618, it lies between 10 and 11 billion light years away from Earth. And it is the most massive object ever observed in the universe. It has approximately 65 billion solar masses. That's the mass it has. In comparison, the Milky Way, if you add up the mass of all the stars in the Milky Way, it is a total of about 64 billion solar masses. So this Ton 618 ultramassive black hole is 100 times more massive than our entire galaxy. That's how enormous it is. And we know that it's so far away from us, about between 10 and 11 uh, billion light years away from us. So the question you ask is, how did it grow this large? Yeah, so for a black hole to grow, there are two processes. Um, Either it accretes mass. For example, if you have a supermassive black hole at the center of a galaxy, it accretes mass from its surrounding areas, and that's how it grows, by absorbing stars, by eating up stars and gas and dust and whatnot, right? That's how it grows. And a black hole that is isolated somewhere, which is not surrounded by mass, if it is large enough, if it is cold enough, that it can grow slowly by absorbing the cosmic microwave background radiation. But that's a very slow process. And like you say, it's not really possible for a black hole to grow this large within the time span of the universe. Our universe is about 13.7, 13.8 billion years old. So, how did this black hole grow this large? That's the mystery. So, one of the possibilities is that perhaps it is the resultant of a merger of multiple ancient black holes, multiple ancient supermassive black holes. So, for example, in the future, about a few billion years in the future, our galaxy is going to merge with our neighboring galaxy, the Andromeda galaxy. And when that happens, eventually the two supermassive black holes at the center of these two galaxies will eventually merge and they'll become a larger supermassive black hole. So it's possible that that is the kind of process that gave rise to the birth to the massive Ton 618 black hole. Maybe a number of supermassive black holes merged in this manner. Maybe it was a region which was a very dense region with lots of galaxies, and this may have been the result of multiple galactic mergers and some sort of cosmic event of that nature or that magnitude. So that is the only possibility that I can think of that would enable a black hole to grow this large. I mean, we have supermassive black holes, but this guy is in a different category altogether. It's an ultramassive black hole. It is like 66 billion solar masses, 100 times more massive than the entire Milky Way galaxy itself. So I think the only thing we can think of is maybe it's the resultant of multiple galactic mergers and multiple mergers of supermassive black holes. So that could be the mechanism by which it was formed. And how did we discover it? Because I'm not sure what was the mechanism of discovery. We would need to have some very powerful telescope. Was it the Hubble telescope? Was it something else? I am not really sure, but uh, one needs to have a very, very powerful telescope that can peer far back into the origins of our universe. So I think this black hole must be below 20 magnitude. So I think the dimmest stars that we can observe with the naked eye must be around magnitude 6 or 7 or 8 or something like that. So this thing must be below 20 magnitude, which means it's incredibly dim. So you need a very powerful telescope to be able to detect this. So most likely it was one of the massive mega telescopes that was able to detect this particular object. Arkadhar asks, do plants get pain when we kill and cut them? If you're a student of biology, you'll be able to answer. Well, I am not a student of biology. I have never really studied biology in great detail. But yeah, well, I have some understanding of biology. I was indeed fascinated with biology at a certain point in time, especially zoology. Botany was a little boring for me, but yeah, this is in botany, but let me try and explain. So we know that plants have an internal structure. We have something called vascular plants. Vascular plants are those plants that transport fluids and various other tissue, whether various other nutrients, etc., from the roots into the various extremities of the plant. So they have an internal vascular structure similar to the veins and arteries we have to some extent. Okay, that's a rough approximation. It's not the right approximation, it's a rough approximation. So if you look at the cross section of a plant, then you have the epidermis, which is the outer hard part, which is basically dead cells. Then inside, one layer deep, you have the sclerenchyma tissue, which is the supporting tissue, which makes plants hard and stiff, etc., which is made up of cellulose and lignin and such materials. Then inside, you have two kinds of transport tissue, which is xylem and phloem. And at the very core of the plant, you have a soft tissue, which is called the pith, which is made up of parenchyma, and it contains starch and various other nutrients. So we know that this is the way transportation happens inside plants, and plants are definitely sensitive to external stimuli, not the way we are. Plants don't have muscles, so they can't move in real time. But if we observe a time lapse of a plant, then you see that it does uh, move around. It does respond to the external environment. Certain plants follow the path of the sun because that's where the sunlight comes from. They need it for photosynthesis. So they do respond to external stimuli. That is a fact. And it is known that plants do respond to music also. This is also an observed fact that has been corroborated by multiple studies. So there is some sort of awareness, if you could call it that, of the external world, and there is some sort of responsiveness to what's happening outside. And we know that plants also compete with each other in a forest, and they try to avoid each other's regions, each other's zone of each other's personal space, so to say, in forests and jungles, etc. So there is some sort of awareness. Now, I don't know whether we should call it consciousness of or awareness or what we would call it. And we don't know for sure what they feel, whether they do feel pain or not if we cut them, because nobody has really tried to investigate this in detail. People even say that that certain animals like crustaceans and lobsters and shrimps, etc., don't feel pain. Well, that is a lie, because you can see the response to hot water. People unfortunately boil lobsters and crabs and shrimp alive for the sake of cooking, right? So you do see the response to that sort of stimulus. They do feel pain. You can see that frantic response. So similarly, it is possible that plants may also have that sort of sensation, if you could call it that. But there is a lack of scientific studies in this field, so we cannot say for sure. But it would be, I would say, it would be naive to say that they don't have any sensations, because they do respond to external stimuli. They do respond to the environment around them. So it is possible that they may feel pain when we kill them or cut them, etc. But well, that is the nature of life. You have to eat other life forms in order to stay alive. That's always been the nature of life on this planet, especially when it comes to multicellular organisms. Certain unicellular organisms are able to uh, generate energy and nutrients from the environment uh, without eating or preying upon other life forms. But in the case of large multicellular life forms like us, we have to eat other organisms in order to survive. So that is unfortunately a fact of life. So if they do feel pain, well, that's just the way it is. So it is possible, yes, that they feel pain, possibly. Sid asks, what's your opinion on scientific institutes having this process called knowledge filter? It means no one accepts a new theory if it is contradicting or if it has enough evidence to replace a well established theory. For example, books like Forbidden Archaeology claim that several archaeological evidences suggest humans may have existed for millions of years. Since this evidence totally contradicts current understanding of when humans evolved, so these claims are put down as pseudoscience or utterly rejected. I believe Max Planck once said, science progresses one funeral at a time. You are right that science has a number of filters. There is something called the scientific method, and there is a very clear dividing line between science and whatever is not science. Things such as philosophy and spirituality and religion, etc., these things are distinct from science. There is some overlap between science and philosophy, etc. Now, it is true that there are very rigorous standards when it comes to new theories. Now, some people claim that humans have been around for millions of years. I am aware that some people have this belief, some people have this claim, make these claims, but the evidence does not stand up to scientific scrutiny. It is very well known that the human chimpanzee divergence happened about 2 million years before today. The fossil evidence shows us that anatomically modern humans evolved about a quarter million years ago, about 250,000 years ago. And from the evidence that I have seen, I have not personally seen any credible evidence that humans have been around for millions of years in the form that we are alive, we exist today, anatomically modern humans. There have been hominins and other species, other older species of proto-humans, Homo habilis, Homo erectus, Homo neanderthalis, the Denisovans, the Florensis humans, Ardipithecus, and many others. But these are primitive humans in the shape and form that we are in today have only been around for about a quarter million years at maximum, from the evidence that I have seen. I have not seen any evidence that overturns this understanding. Now, what is pseudoscience? Pseudoscience is something that makes certain claims, but it is not scientifically rigorous enough. Science has certain standards, and those standards have to be followed. Certain, if you make certain claims, there has to be sufficient evidence that corroborates or validates these claims. Sometimes some people believe that something represents scientific evidence, but it may not be rigorous enough. So the thing is that only scientists can tell whether this evidence is scientifically acceptable or not. Now, you do have a point that certain uh, well, all sciences are to some extent subject to dogmatic thinking and groupthink and all that. For example, in the science of genetics, there is still, even today, this notion. They still are trying to propagate various formulations of the Aryan invasion or migration theory. even though it is now more and more clear that that is entirely untrue. And yet you have these institutes in certain countries that are trying to still push Eurocentric notions. So that is a misuse of science, and they are trying to reject any theory that contradicts their favorite claims. So, yes, you are right that this does exist. Every scientific discipline is potentially falling prey to this. In physics, you have this string theory mafia. I mean, the majority of theoretical physics funding goes into string theory, which has not produced a single piece of concrete or verifiable uh, predictions. Not one. It's not been able to give it even one prediction that can be tested, and a prediction that is falsifiable. And yet you have millions of dollars or billions of dollars being poured into string theory research every year. So that's the kind of dogmatic thinking, group think, etc., that does exist in science. So you are right to some extent, and to some extent, it is also true that lots of these claims are pseudoscientific in reality. Many people who have no understanding of science want to dabble in science, and they come up with all these grandiose claims. So one needs to be very careful in science. The very first instinct of a scientist is skepticism, and that is how it should be. The first instinct has to be, if a new theory is proposed, how do I disprove this theory? Because a theory has to be falsifiable. So to establish the validity or veracity of a theory, it is the job of every scientist who is faced with this theory to try and disprove it, to try and falsify it. So that is the nature of science. You have to try and falsify theories before you can be satisfied that they are true. So uh, these standards are very much there, and they do serve science because they enable the right kind of progress. Otherwise we'll start believing all kinds of nonsense. So this is a complicated thing, right? It's a complicated scenario. We do need all these standards, we do need these filters, but sometimes, many times, these filters are misused when you have these ganging up of certain people with certain beliefs or certain dogmas or certain agendas in science, and then they try and safeguard their citadel, and they try to keep everybody else at bay even when they know that they are wrong. So so it's true. So this works both ways, and basically we need better management of science, right? So that's the thing. Next question. Okay, till there are three questions in here. Till what extent will augmented reality be in use by the end of the decade? What kind of modifications will augmented reality have, and will India use it in the military? So, what is augmented reality? First of all, we have to understand that augmented reality is different from virtual reality. Virtual reality is an immersive experience in which you shut out the real world and you get immersed in a fake make-believe world. So it's like those virtual reality headsets that you wear, in which you go into a different world altogether, a digital world, an electronic world, which is totally different from the real world. Augmented reality is certain visual aids, etc., that you wear, and they superimpose more information on the actual world. So maybe you wear certain kinds of glasses or whatever, and when you walk around, it tells you the name of every building, tells you the name of every street, it tells you the name of every individual is walking on the street, it tells you the make of every car and vehicle that's going on the street, etc. So that is augmented reality. You get more information just by wearing that particular device. So that is something that is slowly coming up. You had Google Glass, for example. Then you have these devices, these gaming devices. What is it called? Pokemon Go or something. I've never played it, but I'm aware of it. And so on. So it is definitely something that has a great deal of real world use. Yeah. And so it could be very much more advanced by the end of the decade. It may possibly be available to the common people out there, certain devices, certain kinds of glasses that you wear, which give you a great deal of information. So you don't have to ask for directions and so on. That is a possibility. So it's all about getting information in real time, which is superimposed on the world. So what kind of modifications will we have? We will have different kinds of wearable devices, perhaps audio devices, perhaps. The most extreme modification you can think of is, neural chips like Neuralink, etc. Excuse me, implanted chips inside your brain itself, which will give you, which may be linked to external devices, etc., and which may give you information in real time. So you don't have to wear something, and yet in your field of vision you see all this extra data. So if you have seen these various science fiction movies like Terminator, then you see that this guy is walking around the Terminator robot, and he's able to see information in real time superimposed on the view of the world. So that sort of thing could be possible if you have these implantable chips which are implanted into the brain. So that is one modification I can think of. So people are going to come up with all these different modifications and different uses of this very nascent technological field. It definitely has a great deal of use in the military. You have, for example, fighter pilots, helicopter pilots who wear these augmented reality helmets. And a helicopter pilot, for example, in the Apache attack helicopter or even the Indian light combat helicopter, they can target their weapons, they can target their guns and missiles just by turning their head, and wherever is this field of vision, wherever the center of vision in the augmented reality helmet, that is where the gun is going to fire or the missile is going to fire. So it makes it very easy to fire at a target just by looking there. That's it. And you also get various other information in in the headset, in the helmet. So this is what fighter pilots are currently using, fighter pilots and helicopter pilots in combat situations. Soon you will have soldiers, infantry soldiers, etc., who will also use these things. So it will definitely be used in the military more and more. India is already using it, I think, in the light combat helicopter and also in the avionics suite of the light combat aircraft, the LCA Tejas. So it will definitely, the kind of use it has in the military will definitely, uh, it will become more and more complex, and it will become more and more an integral part of the military. So that is definitely something that is already happening. It's going to happen further. Abhishek asks, why do like charges repel and unlike charges attract? So that's an interesting question. So why does it happen? Basically, in physics, we sometimes can't really tell why it happens, but we observe that some phenomenon exists out there in the world, and we try and construct a theory that explains how it happens, right? So what we do know, we observe that like charges repel and opposite charges attract. So the theory that explains this is basically, it's quantum field theory, quantum theory. It's a standard model of physics. So in the standard model, we have these particles called bosons, which are the mediator particles. They mediate the various forces. The gluons mediate they are the force carriers of the strong nuclear force. The W and Z bosons are the force carriers of the weak nuclear force. Photons are the carriers of the electromagnetic force, and the Higgs boson it basically endows the universe with mass, and the hypothetical graviton is the force carrier of the gravitational force. Now, the photon has spin 1. The spin is a quantum property. It is the intrinsic angular momentum of the particle. So the photon has spin 1. Now, what happens is that particles which have odd integer spin, they generate forces that can be both attractive and repulsive. But on the other hand, particles with even integer spin generate forces that are only attractive in nature. So the photon has spin 1, which is an odd integer. So this particle generates forces that can be both attractive and repulsive. But the graviton has spin 2, which is an even integer, and therefore it generates forces which are only attractive, and that is why gravity is only an attractive force. There is no repulsive gravity. So it is because of the spin 1 nature of the photon that electromagnetism has both attractive and repulsive components, and that is the basic reason why like charges repel each other and unlike charges attract each other. That is the simplest explanation I can give. Okay, so I hope that explains the question. Okay, Chetan asks. So these are a couple of. I get a lot of questions about radiation, etc. So I've taken a couple of these over here. Chetan says, "Can you explain in simple terms radiation? What causes radiation, and is there any way nuclear energy can be generated without harmful radiation?" So you're asking what is radiation? What causes radiation? And the other question is, how do nuclear fusion and fission reactions work? How do things so small in size cause explosions so massive and are capable of killing humans, which are so huge in size compared to these particles? So these are very simple questions, but it's very hard to explain how these things happen. So let me offer you a quick, short crash course in nuclear physics, because that is the only way I can basically explain these complex phenomena: radiation, radioactivity, nuclear fission, nuclear fusion. So let me share my screen with you, and let me try and make it as brief and concise as possible, but also explain. So I have a different screen. Here we are. Okay. So this is it. So let's start at the beginning. So basically, everything is made up of atoms. Everything we see in the body, physical, in the observable universe, whatever we see, it's made up of atoms. Atoms are made up of protons, neutrons, and electrons. Now, protons, neutrons, and electrons are called subatomic particles. Protons have a positive electric charge, neutrons have no charge, and electrons have a negative electric charge. We find that opposite charges attract each other and similar charges repel each other, like we just discussed. Protons and neutrons bind together to form the nucleus of the atom, and the electrons that surround and orbit the nucleus. The neutrons act as a glue, a nuclear glue, to hold the positively charged protons tightly together in the nucleus. So even though the protons are positively charged, they repel each other. Still, the neutrons, they combine inside the nucleus and act as a nuclear glue, and that's how the nucleus is held together. Now, hydrogen is the simplest atom. It is basically, its nucleus consists of only one proton, and a single electron orbits this nucleus. The helium atom has a nucleus made up of two protons and two neutrons, and two electrons orbit the nucleus. The number of protons and neutrons in the nucleus determines the behavior and the properties of an atom. So that is the basic thing. Now, if you create an atom, if you create a nucleus of 13 protons plus 14 neutrons and surround it with 13 electrons, you get an aluminum atom. And if you group millions of these aluminum atoms together, you get the metallic substance called aluminum. So aluminum has an atomic mass number of 27, which is the sum of the protons and the neutrons in the nucleus. 14 neutrons plus 13 protons is 27 nucleons. So that is the atomic mass number of aluminum. Similarly, carbon has an atomic mass number of 12, oxygen has atomic mass number of 16, calcium 40, and so on and so forth. So hydrogen, helium, oxygen, iron, etc., these are called elements. The periodic table shows the atomic mass numbers and some other physical properties of the known elements. Now, some atoms have extra neutrons. For example, some copper atoms have 34 neutrons, and some copper atoms have 36 neutrons. So atoms with the same number of protons but different number of neutrons are called isotopes. Hydrogen has three isotopes: protium, deuterium, and tritium. Carbon has three isotopes: carbon 12, carbon 13, and carbon 14. Now, certain elements have isotopes that are unstable. In some elements, all the isotopes are unstable, right? So an atom of an unstable isotope is basically, it is unstable. It spontaneously decays into another element by a number of processes. And this spontaneous decay of isotopes is what is called radioactive decay or radioactivity. And the output of this decay is called radiation, right? So radioactive decay produces four different kinds of radiation, four different kinds of radioactive rays. So the alpha rays consist of alpha particles. An alpha particle is basically made up of two protons and two neutrons. It is basically a helium nucleus. Beta rays are electrons, and gamma rays, which are extremely dangerous to human beings and living beings. So gamma rays are very high energy photons, very high energy. So in spontaneous fission, what happens is that an atom actually splits into two or more nuclei instead of throwing off an alpha particle or beta particle. Now, atoms of heavy, unstable elements such as uranium, they undergo spontaneous fission. Uranium is naturally radioactive. It constantly undergoes spontaneous fission at a very slow rate. And other elements such as thorium and plutonium are also naturally radioactive. Right. So when an atom undergoes fission, it splits into two and it releases energy in the form of heat and in the form of gamma rays. And the splitting of an atom releases a massive amount of heat and gamma radiation, and it also releases neutrons. So the two atoms that result from the fission also release beta radiation and gamma radiation of their own. And it's possible to artificially induce fission in uranium atoms by bombarding them with neutrons. So we find that half a kilo of uranium can give off energy equivalent to 5 million liters of petrol. 50 lakh liters of petrol is given off in from half a kilo of uranium. So the fission of uranium can be artificially induced and controlled in machines called nuclear reactors. The most commonly available isotope of uranium is called uranium 238, and the much rarer uranium 235 is suitable for nuclear power. Now, uranium has to be enriched so that it contains at least 3% uranium 235, which is good enough for nuclear power plants. But on the other hand, weapons grade uranium is composed of at least 90% uranium 235. So it needs to be enriched to that level. So nuclear reactors take advantage of what's known as a nuclear chain reaction. You must have heard of this term, nuclear chain reaction. So in a nuclear chain reaction, the fission of one uranium atom causes the fission of more uranium atoms. The first step of a chain reaction is when a neutron hits a uranium 235 atom, splitting it and releasing 2 to 3 new neutrons. Now these 2 to 3 new neutrons hit other uranium 235 atoms. They also split and they release more neutrons. And these newly released neutrons hit yet more uranium 235 atoms, splitting them, and the process continues. And this process continues until all the uranium atoms undergo fission, and this releases an enormous amount of heat. So this is the chain reaction. Now, in a chain reaction, the critical mass is the minimum mass of fissionable material required to sustain a fission chain reaction. And when you have a runaway, uncontrolled chain reaction, that is what results in an explosive release of an enormous amount of energy and radiation in the form of a nuclear explosion, right? So, nuclear reactors control the heat emitted by the enriched uranium, and they use it to heat water and generate steam. So what is done is that uranium is formed into 2 to 3 centimeter long pellets, which are arranged into rods and they are submerged in water. Now, if the chain reaction is not controlled, then the uranium will eventually overheat and melt. This is one of the most infamous photos from the Chernobyl reactor. This is the molten core of the reactor. So that's what happens. It will eventually overheat and melt if the chain reaction is not controlled. So how do we control it? So the heat is controlled by inserting cadmium rods into the reactor. These cadmium rods, they absorb neutrons and thereby they slow down the nuclear fission reaction. So this uranium fuel acts as an extremely high energy heat source. It heats the water and turns this water into steam. This steam drives a turbine which spins a generator to produce power. Very simple. It's basically a steam engine, right? That's all it is. Now, if this reaction goes out of control, the uranium melts and the water and other fluids turn to steam and explode. This results in the explosive release of radioactive materials into the soil, into the water, atmosphere, etc. What you see here is the result of the Fukushima disaster. So this is what happened at Chernobyl, in Fukushima, and 3 Mile Island. Now, apart from uranium, there is another element called thorium that can also be used in nuclear reactors. So India has a reasonably advanced thorium reactor program. Now, there is another kind of reactor called a breeder reactor. It generates more fissile material than it consumes. Breeder reactors, they can breed plutonium from uranium 238, or they can breed uranium from thorium fuel. Now, let's talk briefly about nuclear weapons or bombs. So, nuclear fission bombs make use of the nuclear chain reaction. These nuclear weapons, they are either made up, they either use weapons grade uranium 235, which is at least 90% uranium 235, or they use plutonium. Fission weapons typically have two subcritical masses of uranium 235 or plutonium 239, and they have a neutron generator. This neutron generator is typically a pellet of polonium or beryllium, or maybe both. The simplest way to detonate the nuclear weapon is to fire one subcritical mass into the other. So a hemisphere of uranium 235 or a sphere is made around the neutron generator, and a small bullet of uranium 235 is removed. This bullet is placed at one end of a long tube, as you can see, with explosives behind it. And the sphere or hemisphere is placed at the other end. And the weapon is detonated by triggering the explosives at one end, which fire the bullet into the sphere or the spike or the target. And when the bullet and the sphere come together, they form a supercritical mass. This initiates the fission reaction, and there is nothing to control it. So this is a runaway, uncontrolled fission reaction. It results in a nuclear blast. Now, there is another kind of nuclear reaction called nuclear fusion. So what is fusion? So unlike fission, where a nucleus is split, in fusion, two atoms are brought together forcibly and they are squeezed together and they form a new atom. So fusion reactions give off enormous amounts of energy in the form of heat and radiation. So remember this, that every time you look at the sun, you are witnessing a live display of nuclear fusion. Now, nuclear weapons that use nuclear fusion are called fusion bombs, or they are also called thermonuclear bombs. They are also called hydrogen bombs in some cases. So these thermonuclear weapons, they use an initial fission reaction to trigger a secondary nuclear fusion reaction. So this thermonuclear fission fusion reaction releases hundreds of times more energy than just the fission reaction. So that's a thermonuclear weapon. So now nuclear weapons can either be dropped from aircraft in the form of gravity bombs, or they can be delivered by missiles. Ballistic missiles have very long ranges, and they can be launched from land, and they can be launched from submarines. Cruise missiles, on the other hand, they can carry, they have shorter ranges than ballistic missiles, but they are much harder to detect and to intercept. Now, ballistic missiles can carry multiple warheads using multiple independently targetable re-entry vehicle technology, MIRV technology. This MIRV technology makes it possible for each warhead in a single ballistic missile to be aimed at different targets. And that brings us to an end of this very quick nuclear physics crash course. I hope it was helpful and it made sense. So I hope it answers the questions you asked. These two questions. Okay, next question. Why are we using liquid hydrogen as fuel for rockets, which is so bulky, rather than using nuclear power? It would be a better option. So there are a number of fuels that are used in rockets. One is liquid hydrogen, liquid oxygen. There is also the use of hydrogen peroxide and various other chemical fuels. So there are a combination of fuels that are used in various rockets. Hydrogen obviously is one of the best sources of reactive power in a chemical rocket. But you are right that nuclear power is much more efficient, it is much more powerful. So why don't we use it? Well, the primary reason is that when we use nuclear power, it basically it releases a lot of radiation and a great deal of nuclear fallout. And that is basically very harmful to the environment. It can cause cancer in human beings. It can have lots of long term bad effects. So, that is the primary reason why we don't use nuclear blasts to launch rockets. Actually, what the fact is that such a proposal was made. A study was conducted by the Americans in the 60s, 70s, 80s, I believe, sometime around there. There was a proposal to build a very large, heavy, powerful rocket and send it to Mars using nuclear explosions as the propulsion mechanism. So such a rocket would have to be extremely large, extremely heavy, and it would have to be so strong that it would be able to absorb and withstand the shock of a nuclear explosion. So this was tested out using conventional explosives, and the concept is definitely viable. So it is possible to use nuclear fuel, nuclear explosions, to propel rockets. And these can be very large rockets that can have entire furniture and houses inside them. That's how large they can be, as long as it's made to withstand the shock. But the primary reason is that it will generate a lot of nuclear fallout in the form of radiation and other such things, which is what we don't want. And that is the only reason, basically, why this has not been considered seriously as an alternative to chemical fuel. Akash says, do all the planets of our solar system rotate around the sun on the same plane? If so, why? And also, do all the planets move in the same plane in other star systems? So, yes, all the planets in our solar system rotate around the sun in the same plane. It's like in the Olympics, you have the discus throw, right? A disc. So the solar system is like that. It's in the same plane. Uh, and that is because of the way the solar system was formed. It formed out of a protoplanetary disk. So it was a single disk which slowly coalesced, and that's how the solar system formed. So this is called a protoplanetary disk, a protostellar disk also, and this is something we have observed across the universe in other galaxies. Even in our own galaxy, there are star forming regions in which we can actually witness the birth of other star systems, and you see the same protostellar disk in all these different star systems. You can actually see stars and planets forming, and it's always in the form of a disk. So it is basically this mechanism by which star systems are formed by the uh, by the action of gravity. It is because of that everything is in the same plane and everything goes in a certain direction. So that is the basic reason why all the planets in our solar system are in the same plane. There are certain minor planets and other objects, other bodies in the solar system that are at different inclinations. There is this minor planet or dwarf planet called Sedna, which has a strange inclination. So these could be because some of these objects may have been captured from other stars, or they may have been wandering around the universe and they may have been captured by the gravitational pull of the sun, or maybe there was some ancient impact somewhere between certain objects or bodies in the solar system that may have deflected them into other orbits. But overall, if you see the major planets and the majority of the bodies in the solar system, they are all along the same plane. And it is because of the way the solar system formed, and it is seen throughout the galaxy and the universe in other star systems as well. Aditya asks, can we create anti-gravity outside the laboratory? Well, we can't even create anti-gravity inside the laboratory because we don't even know if anti-gravity exists. From what we know, from what we understand, gravity is only an attractive force. The graviton is a spin 2 particle. The hypothetical graviton is a spin 2 particle. And because of that, the force is only attractive in nature. Gravitational charges, which are the masses, they always attract each other. So we are not aware of any repulsive component of gravity, right? So that is why we cannot even create anti-gravity inside the lab, let alone outside of the laboratory. We do know that there is something called dark energy, which is kind of a repulsive force of some kind, but we don't understand what it is. Is it a fifth force? Is it something else? Is it something that emerges out of the quantum nature of space-time, or is it something else entirely? We are not really sure. Is it a fluid? Is it a form of energy? Is it a new force? We have no idea. Is it in some way related to the gravitational form? That also we don't know as of today, right? The 21st century was supposed to be the century of gravitation, but in 2021 we don't know anything more about gravity than we already knew in 1990. So there has been no new progress happening in this field for the past 30, 40, 50 years. So that's where we are today. So the short answer to this question is no, we cannot create anti-gravity either in a lab or outside of a lab. Sanjeet asks, why is India building a LIGO detector? Does the US partnering with India on the same show that the US government believes in the potential of Indian scientists? So let's understand what LIGO is. LIGO is a gravitational wave detector. It is a L-shaped instrument which spans many, many, many kilometers. It is basically the Michelson interferometer design. It has these laser beams that come together and create interference patterns based on how space-time is distorted by gravitational waves. And these interference patterns show us that a gravitational wave has been detected. Now, there are two LIGO observatories in the United States. One is, they are about 3,000 kilometers apart. We know that gravitational waves travel at the speed of light, and therefore the gravitational signal which is received in one lab will not be received at the other lab at the same time. There will be a small, very small time delay of the order of milliseconds or so. And it is this time delay that enables the lab to determine the position in the sky or in the universe where this gravitational wave source actually is located. So because we have two detectors which are 3,000 or so kilometers apart, that's why, because of the time delay in the detection of the signal, that's why we are able to determine to some extent where the signal is coming from in the sky. Now, the accuracy of the determination of the source will be greatly improved if you have a third detector even further away. And India is a perfect place for that. And that is the reason why the United States is partnering with India to build a LIGO detector in India. So this was approved in principle, whatever it means, in 2015 or 2016 or thereabouts. It's been at least 5 years. I'm not sure what the progress is. I don't know if any construction work has started as of today. The detector is not being basically built in India, it is being assembled in India. The components will be provided from the US. It will be assembled in India, and it will provide the third arm, to the third location on the planet from which gravitational waves will be detected. And it is the triangulation of these three detectors and the different detection times that will enable the determination with a much greater degree of precision of the source of the gravitational waves. So the primary reason why it's being built in India is because we need greater accuracy of determining the source of the gravitational waves, and India is a good location for that. So that is the reason why the Americans are willing to locate a LIGO detector in India. It has nothing to do with their belief or lack of belief or anything like that in the potential of Indian scientists. Everyone knows Indian scientists are excellent. They are the best in the world. It has nothing to do with the belief or anything. It is to do with practicality. They need a third detector far away from the first two detectors. And they would rather not partner with China. And that's why they have chosen India for this. Now, I don't know how long it's going to take for this detector to be built, but it's going to be a good thing for India. Some actual scientific work, even though it's just observational experimental work, but still we will have a world class facility in India for a change. So it's a good thing. Abhishek asks, do black holes engulf photons and accelerate them further? A black hole is most likely a spherical object if it is a Schwarzschild black hole. So black holes don't engulf photons, they absorb photons. And once a photon is absorbed, once it crosses the event horizon of a black hole, it basically disappears. It can never come out, it can never come back. So the escape velocity on the event horizon is the speed of light. The photon travels at the speed of light. So once it reaches that threshold, it can no longer escape from a black hole. So it's gone, it's finished. And once a photon enters the black hole grows just a wee bit in mass, equivalent to the energy of the photon. So that's the amount of growth of mass it experiences when the photon is absorbed. So there is no question of accelerating a photon. Photons can never be accelerated. Photons have a single speed, the speed of light. The speed of light is the same throughout the universe. There is no acceleration or deceleration in the speed of light. The speed of light is the same. It is the global universal speed limit. It is hard coded into the structure and fabric of the universe. So black holes absorb photons, they don't engulf them, they absorb them, and they don't accelerate them, they basically make them disappear. They eat photons and grow larger. So photons mainly of the cosmic microwave background radiation. So that is what happens. Avinash asks, what is the breadth of the Milky Way galaxy? That's a good question. It's always nice to know what are the dimensions of our home galaxy. So let us talk about the dimensions and some facts about the Milky Way. The Milky Way is our home galaxy. We are inside the Milky Way. The sun is located in one of the arms of the Milky Way galaxy. So this is a very ancient galaxy. Its age is about 13 or 13 and a half billion years. It's a very old galaxy. Its diameter is about 200,000 or 2 lakh light years. That's how large it is. That's the diameter. And the thickness of the galaxy is about 1,000 light years. Okay. The total number of stars in our galaxy is about 400 billion. Our galaxy has about 400 billion stars. The mass of our galaxy is about 1.5 trillion solar masses, which includes the dark matter halo of our galaxy. And the diameter of this dark matter halo is believed to be about 2 million light years, or maybe even more. So it is 10 times more than the diameter of the visible disk of the galaxy. So these are some basic statistics about our galactic home. It's a very interesting place. And I hope that answers this question and a little bit more. Harshit says, astronomical research and exploration of our own solar system is understandable, but why are scientists extensively researching about exoplanets, stars, and asteroids of other galaxies, and also calculating the distances from Earth which are impossible to cover? Is it just for curiosity, or will it have any practical significance in the future? Listen, even if we are studying our own solar system, there is almost no possibility in the next century or so of us ever going there. For example, if you take Uranus or Neptune or Jupiter or Saturn, I don't think it may be possible for human beings to reach there in the next century. But someday it may be possible. And that's why we are studying these solar system planets and bodies and all that. Now, why do we do science? We do science to understand the universe. We do it to understand ourselves. We do it to understand our place in the universe, right? And we want to understand how our solar system was born, where we came from, what were the conditions in the early solar system, what is the age of the solar system accurately, what kind of environment did our planet have in the beginning, how did it evolve over time. We want to answer these fundamental mysteries. And one of the best ways of doing this is to observe other newborn star systems outside of our solar system. So if we observe protoplanetary disks and protostellar disks, which are stellar nurseries, then we can see in real time the process of star birth and planetary birth and the birth of a solar system. So that gives us better insights into how our own solar system was formed. It helps us understand our own environment better. It helps us answer the question of, are we unique or are we one of many others like us? It also may someday answer the question of, is there other life out there? Is there intelligent life out there? And so many more questions. There are so many mysteries of the universe we don't understand, and we need to understand them to have a better understanding of where we are, what we are in for, and what kind of future we can envisage for ourselves many generations down the line. So it all adds up. We don't do science only when it is practical. Theoretical physics basically is 100 years in the future. That's the kind of research that is done sometimes. For example, Einstein's general relativity was unproven. It had no actual applications for a century, right? It predicted gravitational waves. The gravitational waves were detected a century after the theory was proposed. And the first practical use of general relativity happened only when we uh, launched the GPS satellites, which use general relativity in order to be in for the accurate determination of locations on the Earth. So sometimes it takes a century or so before your theory actually gives you some tangible results. But it doesn't mean we should not do things that are futuristic or which may not appear to have any practical use today. So that is the thing about science. You always have to pursue science, sometimes for the sake of gaining knowledge in itself. But eventually, that knowledge does come in handy, sometimes in the most unexpected ways. And that is the reason why we are doing all this astronomical research, exploration, and all that you have mentioned over here. So I hope that explains why we do this. Akash asks, are coding skills dependent on the math skills of a person? Saying if somebody is good at maths, will that person also be good at coding? So, coding and programming is basically all about logic. So, a person who has good logical ability, good logical skills, will be good at programming and coding, right? Now, the funny thing is that math is the purest form of logic. It is logic expressed in a certain language, and the language is what we call mathematics. It is the most concise and efficient way of expressing logical patterns and regularities and relationships, and that is called mathematics. So clearly, if you are good at coding, you are good at logic, and if you are good at math, you are also good at logic. So these two skills are complementary skills. Now we find something very strange, that many people who are good at coding are terrible at maths. And why is that? It's because our education system doesn't teach us math properly. To learn math properly, one needs to have a very good foundation of mathematics from the junior KG level itself, from starting 2 plus 2 equals 4, and 2 times 2 equal to 4, and 3 times 2 equals 6. So we have to have a very good foundation of arithmetic, addition, subtraction, multiplication, division. We need to have a very good foundation of algebra, and further on trigonometry, etc., if you want to. But the problem in the Indian education system is that it messes up your understanding of arithmetic itself. It forces you to memorize concepts instead of understanding these concepts conceptually. So many people who will be really good at math because they're good at logic end up being very afraid of math, and they end up hating math. And later on, they find that they're good at coding. So that's the paradox of India's education system. You can learn math on your own without ever needing a teacher, and you can learn coding also on your own without ever needing a teacher. I find that most little kids are brilliant at logic and at math if you teach them properly in a systematic manner. I think everybody is naturally good at math when they are a kid. It's only later on that the education system messes people up. So, to answer your question in short, yes, coding skills are not dependent on math skills, they are dependent on your logical ability. And most people have that inbuilt in them. So, yes, these two different skills are in fact very much complementary: coding and math. Nikhil asks, is it possible that what we call dark matter is actually made up of primordial black holes? Many people have asked me this question. It is definitely very much possible. So, what are primordial black holes? We know what black holes are. I have spoken about this in the past. So, primordial black holes are something that is posited or hypothesized or theorized to have been produced in the very early universe in very large numbers. So we know that in quantum field theory, we have the quantum fluctuations, which are the fluctuations of space time itself. And these are dependent on the energy time relation of the Heisenberg uncertainty principle. So you have particle antiparticle pairs coming in and out of existence in very brief time periods, and you have these quantum fluctuations happening everywhere across the universe, even in vacuum. So in the very early universe, when the universe was very small, very dense, even then you had these quantum fluctuations. And in that very dense state of the universe, certain quantum fluctuations may have caused regions of very small local overdensities, and those overdensities may have given rise to very small microscopic black holes in the very early universe, in the primordial universe. And that's why these microscopic black holes are called primordial black holes. So this is a theoretical thing. Scientists are still trying to search for evidence, observational evidence of primordial black holes. Thus far we have found none. It doesn't mean they don't exist. Maybe we are looking for the wrong thing. So if these primordial black holes were indeed formed, and they are believed to have been formed in incredibly large numbers, then, and if they still survive until today, then it is very much likely or possible that they may form a significant component of the dark matter, which is the missing matter of the universe. It is very much possible. Now, the problem is that black holes undergo something called Hawking radiation. I have spoken about this in the past. So this is a process of basically of the black hole evaporating away. It gives off radiation and eventually it evaporates and dies. It explodes. So this is something that could cause these tiny microscopic black holes to die out, because the smaller a black hole is, the hotter it is and the faster it evaporates. So small black holes, tiny black holes, which may have been formed in the very early universe, they may have died out by now. But there is also the possibility that there's a theory that says that the primordial, any black hole, it may evaporate only until a certain point. It may leave behind a stable Planck mass sized remnant. So if that is the case, then the universe may be littered with Planck mass stable remnants of primordial black holes. So these are all theories. We don't really know for sure. Scientists are still looking for evidence of primordial black holes. Thus far, we have found none, but it doesn't rule them out. So it is very much possible that dark matter may be actually composed of, to a certain significant extent, to primordial black holes, or maybe it may even be composed uh, of bound states of primordial black holes, if those can be stable. So these are all definitely viable possibilities. Aryan Yadav asks, why is going to Mars not a waste of money? Just yesterday, I saw the news that people were eating sand for their survival in Madagascar, and many people are dying in North Korea because of food crisis. So you see these food crises, these humanitarian crises that we have in the earth, we have the money and the resources to solve all these problems. Today there is enough money in the world, and there are enough resources in the world to ensure that not a single human being on the planet has to go hungry. It's just that there is so much inequality in the world, and this is all artificially induced inequality. It is because of this inequality that these problems persist. So certain rich nations want certain parts of the world to remain poor. They want to, I mean, if certain parts of the world are not poor, then how can you show yourself to be superior, right? So these Problems persist because of artificial reasons. Now, when it comes to the progress of technology, of scientific progress and technological progress, that has to continue. Imagine if India had not invested in ISRO in the 1960s and 70s. Today, India would be far behind technologically. We would not have access to all the satellites that we are able to put into space of our own volition. We would have to rely on other countries to launch our satellites, and they would charge immense amount of money. And they may do a bad job of it if they want to, or they may refuse to launch certain satellites, for example, military satellites. So all of the space resources that we are able to enjoy and benefit from today, for example, in the field of agriculture and many other things, which actually benefits the poor people of India, that would not be possible had India not invested in space and in the space program. And therefore, all of this that we are doing, even the Chandrayaan mission, the Mars orbiter mission, these are not waste of money. These are improvements in our technology, and these will benefit the country in the long run. It will not benefit us today. But short term planning is myopic planning. It is short sightedness. You have to always plan in the long run, 30, 40, 50 years ahead. The Chinese plan 100 years ahead. And that's why they are where they are today. They are where they are today at the cusp of being a superpower and at the cusp of solving all their poverty, because they started planning like this 50 years ago, when 90% of their population was below the poverty line. So it is only because they planned like this and they invested in science and technology that they are able to progress so much. And today, almost nobody in China is below the poverty line today. So all of this is a valuable and worthwhile investment, provided the result of this investment is reinvested back into the country and it is used to solve the country's problems. So that is why I believe that I am firmly and strongly of the opinion that science and technology must keep progressing. You cannot put it on hold and solve the other problems. Even in India today, all the poverty which still exists is actually solvable in 5 years. If the politicians will stop bickering among each other and stop using poor people as vote banks, right? So poverty is maintained in India. Slums are maintained by politicians in India because these are captive vote banks. This can all be removed. All of these, this suffering and poverty and all of that can be alleviated within 5 years if the Indian politicians really want to. So it is not a question of wasting money on space and other things. It's a question of basically reforming your own terrible system. That's all it is. That's why I would strongly say that going to Mars or going to the moon or going to space is not by any means a waste of money. It is an investment in the future of our children and our grandchildren. It needs to happen. Chiranjit asks, if there exists a cosmic microwave background, why is there no cosmic radio wave background, as radio waves have longer wavelengths than microwaves? So to answer this question, we have to understand what is the cosmic microwave background. The cosmic microwave background is what remains of the first light that was born in the universe. So the first light of the universe came into existence about 300,000 or so years after the Big Bang. It's when the universe first became transparent. That's when photons started to travel, and that's the origin of the first light in the universe. The universe was very hot at the time, and this light was very energetic. It had very short wavelengths. And then, as we know, the universe expanded, and it cooled. And because of the expansion of the universe and the cooling of the universe, the light also uh, became cooler. It became less energetic because of redshift. As the universe expands, as space-time expands, the wavelength of this primordial light also stretched out. And that's why from very energetic light, it became less energetic because the wavelength became longer. So as of today, it is in the microwave length. The wavelength is in the microwave region. Maybe a few billion years in the future, as the universe expands further and more redshift happens, these photons will in the future be in the radio wave domain. So it will happen in the future. As of today, it's or the universe is only 13.7, 13.8 billion years old. So these old photons, these primordial photons, have only had the time to come down energetically into the microwave wavelength domain. In the future, they will go down further in energy, and they will surely reach the radio wave frequency domain. So that's what will happen in the future. Right. So that brings me to the end of these questions. Let me now take a look at your comments. If you have any questions, ask me now. No history questions, please. Only physics, science questions. Let us see. What do we have? Bharat asks, does darkness travel faster than light? Darkness isn't a thing, it is the absence of something. Darkness is the absence of light. Darkness doesn't have a speed. It is simply the absence of photons. So darkness doesn't travel. It is simply what our mind perceives when there is no light. So it is not a physical thing. It is something our mind constructs. It is something our perception and our consciousness constructs to fill in the blanks. So when there are no photons, our brain interprets that as the color black. And that is what is darkness. So darkness is not a real thing. It is something that our brain creates in order to fill in the gaps in whatever is absent in the world. So it has no real speed. Ayush says, can you tell us about the electromagnetic property and the gravitational property of dark matter? So, from what we know, dark matter interacts only gravitationally. It is some kind of particle or substance that only interacts gravitationally. It does not interact electromagnetically. So the entire world that we perceive around us, all the stars, all the planets, all the galaxies, all the nebulae, etc., these are all made up of baryonic matter, which interacts electromagnetically, and that's why we are able to see it, because of the electromagnetic interaction this matter has with photons and the universe. So that's why we are able to see it. Something that doesn't interact electromagnetically cannot be seen with our eyes, because our eyes are receptors of electromagnetic radiation, which is photons. So this dark matter does not interact via the electromagnetic interaction. It only interacts gravitationally. So we can feel its gravitational effects, but we cannot see it. So to answer your question in short, it has no electromagnetic properties. It only has gravitational properties, the properties of mass. Okay, let me see one more question. Neeraj says, why are the scientists only busy in exploring life on Mars and not making Earth environmentally a better place to live for generations? Mars isn't a solution to life for every human being. You are right. Mars isn't the solution for every human being. So I would not agree that all scientists are busy exploring life on Mars. There are lots of scientists who have nothing to do with Mars or with space, right? There are so many different fields of science. For example, electronics, quantum computing, artificial intelligence, materials science, and so many more have nothing to do with space exploration. And they are trying to develop new technologies, etc. But it is not in the hands of scientists to make the world a better place. Scientists discover new science and new technology, they invent new things, but it is for the governments of the world to use these tools that science gives us to make the world a better place. Scientists are not in charge of doing this. A scientist has no power. It is the politicians, the governments who have the power to either change the world for the good or for or for the worse. So it is the governments which have thus far failed to do it. It is the governments of the West that have created the environmental crisis that we are now seeing. Climate change is a result of the past two, three, 400 years of pollution, which started from the time of the Industrial Revolution in Europe. And what we are seeing today is a consequence of these centuries of pollution, of the atmosphere, of our rivers, of the soil, etc. And all the plastic that we see in the oceans is also all that was dumped by these affluent countries. And it is their governments which have these policies of dumping all of this material into the oceans, into the atmosphere, and all that. So it is the politicians and the governments who have implemented these policies. Scientists have only one objective: they want to understand the world better. That's the research they do. A space scientist and astrophysicist will try and understand the stars. A material scientist will try and develop new materials. A quantum physicist will try and develop new quantum phenomena or new quantum technologies, and so on and so forth. Every scientist has a for certain field of specialization, and that's what they work in. But that's all they do. They do research and they develop new things. It is for governments and politicians to use these tools to make the world better, and that is why the world is not better. Right. And I agree that Mars is not the solution to the entirety of humanity. Only the super rich will be in a position to go to Mars maybe 30, 50 years down the line. It is not the solution to humanity. The solution is to manage our planet better. So that is what the governments and politicians are not doing. Now it's well known that climate change is a reality, and still there is no consensus on how to deal with it. So it is not the fault of the scientists that this is happening, it is the fault of the governments. Okay, one more question. Gaurav asks, I feel that when we die, another reality timeline can be formed in which once you are dead, another you are alive at the same time. So it's called the many worlds theory, the many worlds interpretation of quantum mechanics. Uh, every decision that you make, every action that you take, every choice that you make splits the universe into two branches, and maybe in one you continue to be alive, in another you are dead. So it is a possibility. It is the many worlds interpretation of quantum mechanics. So it is not proven by any means. It is just a hypothesis. It is one interpretation. So I don't know. As a scientist, I rely on observational evidence. When you have a theory that is not falsifiable, you basically don't take it very seriously. It is definitely something that is considered to be a viable interpretation of quantum mechanics, but it is not falsifiable as of today. Therefore, it is a hypothesis, it's not a theory. Okay, one last question. Is there any way to slow down human aging? Yeah, there is some research that's being done into the telomeres. So telomeres are the structures at the end of chromosomes in the human cells, right? And these structures called telomeres, it is found that as a person gets older, the length of the telomeres decreases, and this is nowadays believed to be what contributes to human aging. So it is believed that if you can find a way to stop the shortening of the telomeres, then you can possibly pause the process of aging, or you may even be able to reverse it. So this is a theory, and some research is being done into it. I'm sure it's a very lucrative thing. If somebody can find a cure to the process of aging, then it would be a very lucrative thing. So this research is happening in various places. As of today, I am not sure that they have actually found a way to either stop aging or slow it down or to reverse it. But it is something that is definitely being researched. Okay, my friends, this brings us to the end of today's session. Thank you very much for your questions. Thank you very much. I appreciate everybody's participation. Thank you to everybody. And so I will see you in the next session, which is history, tomorrow. Until then, take care and have a good day. Have a good night.